The simple phenomenon of wind turning a turbine blade to light up a home miles away represents one of the most remarkable achievements of modern green technology. While the concept sounds straightforward, the journey of transforming kinetic energy from moving air into high-voltage electricity relies on an intricate combination of physics, mechanical engineering, and electromagnetic science. Understanding how a wind turbine operates requires looking deep into the natural behavior of wind, the aerodynamic design of massive modern blades, the complex machinery inside the nacelle, the physics of electrical generation, and the delicate power transformation process that ensures energy arrives safely and efficiently at its final destination. It all begins with the source itself, atmospheric wind. Wind is fundamentally created by the uneven heating of the Earth's surface by the sun. As warm air rises, cooler air rushes in to fill the void, creating continuous air currents. This moving air possesses kinetic energy, which is the energy of motion. To capture this energy, wind turbines are constructed at immense heights, often elevated hundreds of feet above the ground. Higher altitudes are selected deliberately because wind speeds are consistently stronger, smoother, and less turbulent up high, away from trees, buildings, and ground friction. When these powerful winds encounter the large blades of a turbine, a crucial aerodynamic process occurs. Contrary to popular belief, wind does not simply push the blades around like a paddleboard in water. Instead, turbine blades are meticulously engineered in the shape of an airfoil, similar to the wings of an airplane. As the wind flows over the blade, it is forced to move faster across the curved top surface than across the flatter bottom surface. This difference in airspeed creates a pressure differential. Lower air pressure forms on top of the blade, while higher air pressure remains underneath. This disparity creates an aerodynamic force known as lift. Because the blades are securely fixed around a central hub, this lift force pulls the blades sideways, causing them to rotate around the central point. Modern three-blade designs are mathematically optimized to balance aerodynamic stability, structural weight, and energy extraction efficiency. As the blades spin, they drive the primary mechanical components housed inside the nacelle, which is the large structure sitting atop the turbine tower. The rotating blades directly turn the low-speed shaft. However, the blades themselves rotate relatively slowly, usually between 8 and 20 revolutions per minute. This speed is far too slow to generate a usable amount of electricity directly. To resolve this mechanical challenge, the low-speed shaft feeds into a heavy-duty gearbox. The gearbox acts as a mechanical amplifier, dramatically increasing the rotational speed. By utilizing a precise arrangement of internal gears, it converts the slow, high-torque rotation of the main shaft into a high-speed rotation reaching roughly 1500 to 1800 revolutions per minute. This high-speed shaft is then connected directly to the generator. The generator is the core component where mechanical movement transforms into electrical energy through the principles of electromagnetism, first discovered by Michael Faraday. Inside the generator, powerful magnets and densely wound coils of copper wire interact with one another. When the high-speed shaft spins the generator's rotor, it causes a magnetic field to continuously pass over and move through the stationary wire coils. This constant movement of magnetic lines of force disrupts the subatomic particles within the copper wire, forcing free electrons to flow in a uniform direction. This stream of moving electrons constitutes an electric current. Thus, the mechanical energy captured from the wind is officially converted into clean, alternating current electricity. However, the journey of the newly generated electricity is far from complete. The electricity exiting the generator is typically produced at a relatively low or medium voltage, usually around 600 to 1000 volts. Sending electricity through power lines at low voltage over long distances is extremely inefficient. Electricity naturally encounters resistance when traveling through physical conductors, such as copper or aluminum wires. This internal resistance causes a significant portion of the electrical energy to be wasted and lost as heat. If power companies attempted to transmit low-voltage electricity directly from the turbine to cities miles away, a substantial amount of the harvested wind power would disappear into thin air before reaching a single light socket. To overcome this fundamental physical obstacle, the electricity is immediately routed through a transformer. Modern wind turbines typically feature a step-up transformer located either inside the base of the tower or in a small housing right next to it. The transformer operates on the principle of electromagnetic induction. It consists of two separate coils of wire wound around a shared iron core. The primary coil receives the low-voltage electricity coming from the generator, while the secondary coil outputs electricity at a significantly higher voltage. By having many more turns of wire on the secondary coil than on the primary coil, the transformer steps up the voltage, increasing it to thousands or tens of thousands of volts, while proportionally decreasing the current. Raising the voltage drastically reduces the electrical current moving through the wires. Because heat loss during transmission is directly proportional to the square of the current, reducing the current is the single most effective way to eliminate energy loss over vast distances. With its voltage boosted to high levels, the electricity can travel out of the turbine, through underground cables, and into a central regional substation. From there, it enters the high-voltage electrical grid, traveling effortlessly across countrywide transmission networks with virtually no loss of power. When the high-voltage electricity finally reaches towns, cities, and neighborhoods, localized step-down transformers reverse the process, safely lowering the voltage to standard levels suitable for household appliances and commercial machinery. Every single phase of this process operates seamlessly under the continuous supervision of advanced automated sensors and computerized control systems. Wind vanes and anemometers mounted on the turbine continuously monitor the direction and speed of the wind. If the wind direction shifts, small yaw motors rotate the entire nacelle to face directly into the oncoming breeze to maximize power capture. If the wind becomes dangerously strong during severe storms, computer systems automatically pivot the blades out of the wind to stop rotation, preventing structural damage to the machinery. From capturing air currents through lift-based aerodynamics to generating electrons via magnetic fields and boosting voltage through transformers, the wind turbine turns a simple gust of air into a highly efficient, clean, and continuous source of power for the modern world.